Okay, welcome back, and I think this will be the last video that we do for this section, and just wanted to go through a few derivatives of trigonomic tables. So it's important for us to be able to do the chain rule in a number of different settings, not just algebraic. So again, the emphasis is on the chain rule, and it's just this whole idea of we're still going to have dy dx. There's no problem with us having dy dx and getting through some other pronumeral set to help us get dy dx. So whether it's y, and we're formulating these new equations to help us do that. Okay, so whether we do that, however we do that, is doesn't matter as well. All right, so in terms of our trig, we're now being told what these are. So the different, I did that as an empirical example. So now we've got these other results that we can rely on as well. Okay. All right, so straight off, we're looking at a chain rule. So this is the beauty of this. I think I'm just going to go like this with this one. So the chain rule is going to be invoked because x is having two things done to it. X is being 3 times 3 and cos. So if we rewrite this as y equals cos 3x, we still have to let u equal 3x, and y will be equal to cos u. So now we've got a y in terms of u and a u in terms of x, and that's what this little table at the top was. Okay, y in terms of u and u in terms of x. Okay, so now what we'll do is we'll go ahead and we can do the differentials. But I want you to do it this way. I don't want you to do it any other way, because this helps you remember what the chain rule is, leaving its notation. Okay, now we've already learned the differential of sine. It's cos, so the differential of cos is minus sine. It's on the table. Okay, minus sine. Differential of cos is minus sine. Doesn't matter what the pronumeral is. Okay. The differential of 3x is 3. Goodness gracious me. Okay? Wow. So put them together, and dy dx is going to be dy du dx, which is going to be minus sine u, which itself was 3x, times 3. Okay, so we're going to get minus 3 sine 3x. Now the temptation is to use a shortcut. I strongly advise you not to do that. Okay, let's try this. Let's say the question said it this way. dx cos 3x. What? So we're differentiating an equation over here and an expression over here, but it's still the same process. Okay, so we would let u equal 3x, leaving its notation would require us to find this. Now we would ask d du of cos u, because that's the substitution that was made. Okay, and now notice where the equal sign goes at the end. Look at this. This one goes here. The equal sign goes at the end. So the du dx is 3, and the d du of cos u is minus sine u. So we're still going to have d dx. We're just going to go through something else to get it. And the something else we're going through is du dx. So that's now minus sine u times 3, which is equal to minus 3 sine, and u was 3x. It's the same answer. Same answer. Okay? So whether you do it as an expression or as an equation is entirely up to you. And just be careful with these. This means the cos of this argument. So in this case here, we're going to let u equal x cubed. Y can then be rewritten in terms of u. There it is, you see. So dy du and du dx. And you'll get used to them. Du dx is 3x squared. And dy du is the cos. Now we just did the cos. So the cos of something is minus sine. And u. And we put them together. Dy dx. And we get 3x minus 3x squared sine. And u itself was x cubed. Okay, you can check those. So please be careful how you lay these out because it is very, very important. And once again, d dx cos x cubed. Let x cubed u dx. Then ask the question d du of cos u. That will be equal to minus sine u. Putting them together as a chain gives you d dx, which is equal to minus 3x squared sine x cubed. It's the same. Now be careful with these because convention tells us that we can write this way. Okay, they're vice versa, same form. Check the form. They're equivalent forms. Okay, so in this case here, we would let u equal cos x. Oh, so y would be equal to u squared. Be careful there. Okay, so dy du and du dx. Okay, that'll be 2u. Calculus is done in no time flat. And we've also learned that this is minus sine x. So putting the two chains together, our differential dy dx is equal to, now u was cos x. So look what's going to happen with this. This is going to become 2 lots cos x times minus sine x. Now I've just put the bracket in to show you that it was the term sitting next to the 2. But in actual fact it doesn't need to be like that. Okay, so quite advanced work when you're using the chain rule. Okay, quite advanced. So the question might present like this. d dx cos squared x. What? Well, that simply means d dx cos x all squared. So let u equal cos x. U dx will equal minus sine x. Then that begs the question d du u2, which is equal to 2u. This one is minus sine x. Okay, putting the chain rule back together, d dx is d du u dx, which is minus 2 cos x sine x. Same as this one. Okay, so whether you do it in an equation or an expression, doesn't matter. Okay, we'll go over these particular ones again. Alright, so we've got the same thing, sine squared x. What's going on with this? This means sine of all of the argument, all squared. Now this is a very typical first test in Maths 1. Are you listening? You won't get an easy one like I'm giving you. You'll get this one. And this is a triple chain rule. Okay? So we're going to let m equal all of the bracket sine 12x plus 1. Now, why have I done that? I can write this as y equals m2. I don't understand why he needed to do that. Well, look, this one here, to find the differential of this, requires us to find the differential of this one. This is twice. This is another one. So x is being 12 plus 1 sine. So it's actually requiring us to write let n equal 12x plus 1. And that will allow us to write m, not in terms of x, but in terms of n. So now we've got y in terms of m in terms of n in terms of x. 3 steps. 1, 2, 3. That means we've got a chain rule that goes dy dm, dm dn, and dn dx. Okay? dm dn. 3 chains. So dy dx. We're still going to have dy dx. We're going to go through 3 things to get it. dy dm, dm dn, dn dx. Okay, that's going to be our rule. So we need to do this. 2m, which is sine 2 lots of sine 12x plus 1. So there's a lot of writing in this one. Now, the differential of sine is cos n. But n is 12x plus 1. Okay, so we're just putting it all together. And this is 12. So we've got 3 products. 1 times another one times another one. So 2 sine 12x plus 1 times minus cos 12x. Now, what have I done there? Why have I put a minus there? I didn't need to do that. Differential sign is cos, leave it. So that's fine. Cos 12x plus 1 times 12. So we're going to get the numbers multiplying. 12 times 2 is 24. Doesn't matter what the order you put it in. That's it. So we check it with Wolfram. So it'll understand this actually. It'll do it quite well. So we can do sine to the power 2, then put our argument of 12x squared plus 1 and Wolfram should be able to see that and for what it is, and so it gives you this sine 12x squared cos. Now 48x, I think I've made an error there. Let's see. 12x is 12. Sine n, differential sign is cos. So, that's an equal sign. Cos 12x plus 1. And this was sine. M was sine 12x, so that's 2 lots of that. So 24 sine x. So why have we said 12x squared? M squared. So I think we're right. 2 lots of sine 12x. times cos 12x times 2 Just checking that. Just want to see what I've done there. So I agree with this. So it's presenting it in a slightly different way, you see. Is that 12x or 12x squared? Right, 12x squared plus 1. Left it off. Look, I'm a bad man. Okay, so that's 12x squared. 12x is easy to do. 12x squared. Oh dear. 12x squared, so that's actually 24. Okay, I can hear you screaming at the TV. Jason, you missed the square. So that's 24x. That's 24. Okay. So that's 24. So that's good. Other than that, we're all good. 12x squared. So they just become the x squared terms. That's fine. Doesn't fundamentally affect it. But it is 2 lots of 24, which will be 48. So see, it's easy to make a little transpositional mistake. All I did was I didn't put the x squared in when I wrote it. So, and I did it all the way along. The only thing it affected really was this differentiation down here. So other than that, we're all good. I'm glad I spent a bit of time looking at that. Okay, so that we could validate this whole thing of, 48 sine. So that's important. And that'll be x as well, mate. So just put those in. Make sure you get all of those in. Okay. Simple little transposition. So rewrite, because there's going to be 10 to the 7x to the power of a half. So we have to do the same thing again. We have to let m equal everything. 10 7x. Y will then be in terms of m, but this is a chain rule. So we have to let n equal 7x. So now n is 7x, so m is the tan of n. So far so good. So dy dm, the m dn, and dn dx. So they'll all chain together to give us our final result. So that'll be 7. Now, the differential of tan is sec squared. And we'll put the n in for now. Half m half minus 1 is half m minus a half, which is 1 over 2 to the square root of m. So that's fairly straightforward. So they're our products. So the 7 will go on the top. So dy dash will be equal to 7 sec squared n was 7x divided by 2 the square root of m, which itself was 10 n 7x. Okay, so it's worthwhile checking. Differentiate the square root of 10 7x. So differentiate the square root of 10 7x. 7 sec squared over 2 the square root. So we've got the same result, which is great. So it's important to recognise that this requires practice. It's not something you can just wolf down very quickly. But again, these are more representative of what you need in Maths 1. So that's why we're doing them. Okay, so for differentiation, this is a product rule. U and V. See that? A product rule. So I'm going to come back one more video to get this done, I think. One more video. Oh, we might do logarithms next week. I think we'll do logarithms next week.